Thank you very much. And thank you very much to everybody at ScrumTech for making this huge online event possible and for inviting me. I'm sorry I don't speak any Russian, so you have to come by with me talking in English. If you got any questions during the talk, I'd be most happy to answer them in the chat, maybe afterwards, because the talks are scheduled pretty closely. Right. About 70% of all our time in software development we do spend with improving or changing legacy systems. That means existing systems. So we better think about a systematic way of doing that. I brought you some ideas. We got limited time, so we speed up. My name is Gernot Starke. I'm a software architect since many years. I'm software engineer, software developer since even more years. And yeah, I was really happy to be talking at a Russian conference because I've been to a Russian conference a very, very long time ago. One of the best events I've ever been to was in 1993 in Moscow. That was the invitational poster. I drew that myself because I'm playing a saxophone a bit. But don't talk about history. When we change or improve or modify existing system, there should be only one reason we do that. That's adding value. It's not because we just want to do something, or we heard that the new framework XYZ is a cool framework. We should not change system because other people are moving to the cloud or whatever. So we should look for business value only. And I can accept bad source code if we never change it. So we can leave the bad source code. Really make sure you think about value before you start changing systems. And one aspect of adding value is removing problems. And that's actually what we will be talking about today, is adding value by removing problems. Problems in your system, in your software, in the processes around your system, and so on. And that is what we are doing most of our time. Yes, we are also adding value by adding features, but that's another story. Should be another talk. But now we are talking about removing problems. What about problems? You are building complex and complicated systems. You are not building Hello World. I mean, in Hello World, probably there are no problems and you got all the problems inside, and that's not difficult. But if we are talking complicated systems, more complex systems, it's interesting to think about what kind of problems can occur. I brought you an example from real life. Look at some vegetable soup, whatever. That's a complicated system. There are various stakeholders involved. There is different types of problems you can encounter. That's just an analogy to software. As in software, it's even more complicated, but let's look at the soup. You might have problems with the taste. It's probably too salty or too hot or not tasty enough, whatever. You might have problems with the price. So compared to the restaurant you serve the soup in, the soup might be too expensive, or the price doesn't cover the ingredients, doesn't cover the price of cooking, whatever. Maybe the soup is delicious, but it doesn't look good. That's a completely different type of problem than the taste. Maybe the soup looks good, tastes excellent, has a reasonable price, but your restaurant is located in the middle of nowhere and nobody's going there. That's another type of problem with your soup. It goes even further. Maybe the soup is too hot, or it's not hot enough, or the consistency of the soup it's too liquid, it's too stiff. You put the spoon in and cannot get it out because it's Maybe you look at the soup from a completely one more different angle, and you try to analyze the ingredients, and you find out that the soup doesn't contain any proteins, or it contains too much fat or not enough fat, or it doesn't contain any vitamins. Or probably you go even one step further. My kids, they are grown-ups, they are doing sports, and they do sports on a German championship level. So they have to look for forbidden ingredients, as they are not allowed to take any ingredients that are on some doping list. So when they go to a restaurant, they sometimes ask for specific ingredients not to be contained in the soup. I personally never thought about such a problem, but it might be a problem. So you could even analyze your soup in a lab. That's still not all kind of problems. It might be difficult to get decent tomatoes or decent ingredients. Maybe you want to large scale produce your soup, and you need a huge kitchen, or you need huge amounts of ingredients and have no room to store it. So logistical or storage problems connected to your soup. In software, we have to tackle these various types of problems. And I brought here an image of a very small child, and I call beginners in software development. Often I like to compare them to children, because children, they have a very narrow field of vision. That's organical. They cannot do anything against it. They focus and they start running towards any goal without looking left or right, because organically they cannot do that. They can only focus. And beginners in software development often have a very, very narrow focus on very specific topics and talk only about these and tackle only these types of very narrow-minded problems. And as a professional, more experienced development team, I really urge to do a methodical overview with a very broad range of vision, what kind of problems you have. Not only focus on very tiny code problems, there might be more difficult, more important, more value reducing problems than the little ones the beginners only see. When you found the problems, you need to prioritize, because you won't have time to fix all the problems. That's a way of life. In open source, you might fix all the problems because you have time enough. You are not limited by any budget. In reality, I am always limited by a budget. And finally, when we've done that, we had a look at the problems, we found out decent priorities, then only we should start modifying or changing or improving the system, because then we have specific problems to solve. I hope you're with me on that. Now, this idea of finding problems, getting priorities, and only then improving is pretty old. We've created an open source methodology for containing good practices around this way of improving systems. It's called Architecture Improvement Method. It's very easy to advertise for open source, because you can have a look at it. If you like it, use it. If you don't like it, don't use it. It's aim42.org, 42, the magic number, from this very strange science fiction book you might know. Architecture Improvement Method. The first step is finding problems. I call it breadth first search. As we don't only have problems in source code, we might have the wrong people in a position we might have a wrong architectural decision, a wrong structural decision. We might use bad technology. So the cook put bad tomato in the soup. Although the recipe is fine, bad idea. So breadth first. The breadth in software is really huge. So I brought 10 aspects of breadth first search with me. I'm sure we cannot cover all those in the short talk, but I brought examples from most of these, so you might get an idea what I'm talking about. The first area where I want to look for problems is people. I want to talk to people as people experience the problem. As a developer, I want to talk to developers. What kind of problems do you as developers see in your source code, in your system, in your transition from requirements to source code, in your transition from source code to productive code, from the source code, do you have an automated way into your app store, whatever. Stakeholders know about many solutions. Probably they don't have the budget to implement the solution, but you could at least ask. Let's move forward. You talk to some stakeholders. In analyzing systems and trying to find out system, one thing you should always do is look at the overall structure, the overall, let's call it component structure or subsystem structure, the higher level building blocks of your software. That might be packages in a Java system, that might be namespaces or Maven modules, that might be Python modules. Whatever technology you're using, you can identify high-level structure. One question to ask is, do you have overly many components? Do you have overly many dependencies? So is your coupling too difficult to understand? Does it lead to a high cognitive load so people cannot understand your structure? Whatever. I brought an example, a real-life example from a very, very huge e-commerce system with millions of users. It's not from Germany and it's not from Russia. It's from a company working in Central Europe. Actually, it's selling train tickets. But without giving any details, you see a component structure. That's a real component structure. And the components have been built with a fairly large number of different technologies. The original system was built on a mainframe. It has been worked upon for a very long time. Currently, you have the mainframe backend. You have a mobile, Android, iOS, mobile app front ends, but you also can buy these train tickets in shops, on train stations, wherever. And you have an overly large number of different technologies with all those difficulties in getting your data from some Python backend service to your COBOL mainframe service, and it's a really mess. The system works well if you look at single of these modules. The code quality is quite okay, but from the overall perspective, it's a disaster. It's a real disaster. It's actually what some people call a deployment monolith. So deployments happen every few months only, not minutes, as I would like to have it, but months. Really historically grown bad overall structure. You won't see this, you won't recognize this if you only look at small parts of the source code. So that's an example for another kind of problem. Now, actually, we are working on source code most of our time. So it pays off to have a look at detailed problems in source code. You will know how to do code reviews, so I don't want to talk about code reviews in detail, but I want to pick out one interesting aspect. Okay, you can measure code complexity, cyclomatic complexity, levels of loops, whatever, if else, nested, it's difficult to understand. That's good if you measure it. But even better than these simple measures, I experienced combined metrics. So if you have a look at complexity and you overlay this complexity metric with change frequency, for example, then you might come up with graphs like the following. I copied this from a very nice book from Adam Thornhill. I should give you the link in the show notes in the description. The link is on my slides, so you get the slides afterwards, after my talk. He had the idea of combining various metrics, for example, change frequency and code complexity. Why that? If you change anything very often, you add up this tiny little risk that something might go wrong, change risk. If something is really complicated, it's really difficult to understand, the change risk is very high. So if you have complicated parts of a system that are changed very often, the risk of something going wrong is really high. And you can measure change frequency by analyzing your code repository like Git or Subversion. Very easy to do. You can measure code complexity by applying any complexity code metrics. And this guy, Adam Thornhill, had the idea of combining those into nice graphics. There are some open source tools that allow for this type of analysis. And I used this in several commercial projects and was really able to pinpoint so-called hotspots, parts of the code that were really problematic. Very nice to identify problems that are worth solving. Now, let's move forward to one more typical area of problems. I call this external interface hell. In one of my systems I worked with, we had craftsmen, electricians, people doing real work with real things. And in our e-commerce shop, you could configure complicated products like desks or others. And we guaranteed that these things could be brought to your home, and you get some craftsmen to help you build this actual thing. So you don't need screwdrivers and a hammer to do it yourself. But this shop had many of these craftsmen to ask for availability, for example. And they had initially they had come up with the idea of building a standards API, so these craftsmen can connect to the system. And from the more than 200 of these external systems, only some 30 were using the standard API, and the 160 something had point-to-point integrations. 160 or approximately 200, as written on the slides, point-to-point integrations to external systems. What a mess. What a huge mess. Every single of these integrations might be of very high code quality, might be easy to understand, but it's non-standard. So somebody had to implement this specific external interface, had to invest time, money, had to write test cases, and you can imagine that these external things change from time to time. You, as system provider, as development team, have to cope with these changes. And you don't want to depend on 200 external systems changing continuously, and you have to maintain all these point-to-point interfaces. Although code quality, code metrics of these single code elements was quite okay. So a stupid or overly simple code analysis would reveal the code is okay. Looking specifically at these external interfaces revealed the huge maintenance problem that obviously the developers knew, but we had to explain to management that if you want a standard API, you should only use this standard API and not allow overly many point-to-point integrations. So next thing to look for, I call this cohesion. Cohesion is a very strange term that means, does something belong where it is? So do things belong together or should they be separated? I have an example. That's from real life. Again, one of these e-commerce systems I quite often work in. And this e-commerce needs a pricing, some component to determine the price of a product. In larger online shops, it's sometimes a bit difficult to determine a price because people have vouchers. So you have to reduce the price by some voucher. People have some gross contracts. So if they buy thousands of products per year, they get some reduction of certain percentage on certain types of products. There might be reductions for specific marketing occurrences. There might be reductions for specific age groups. It's a mess. It's really complicated. This system had a component handling much of this complexity. They had called it pricing engine. And I came into this project as a new developer or architect. My expectation was the code for calculating prices is contained in a component named pricing engine. But that was not the case. Much of these pricing rules, business rules determining prices, was contained in other components. So what happened one day, that's a real life story, the pricing engine determined a price of 0. So they gave away the product for free because the pricing engine calculated, oh, it must be 0. We analyzed, we debugged in the pricing engine and couldn't identify this problem. Every pricing rule in the pricing engine was fine, was implemented correctly, but still the final price was wrong. It took us a very long, overly long time to identify that certain price pre-calculations done in other components, as you see here on my graphics, in components named completely differently, shouldn't be there. It was an example of a very bad cohesion. So code belonging to price calculations was located in completely different parts of the system. Actually, the pricing was written in Haskell, in functional programming language, and much of the older pricing code was written in Java and Python and even in COBOL. Very bad idea to spread responsibility for a specific task all around your system. So that's one more aspect or area where to look for problems. Let's move the code away altogether and have a look at application data, or more specific, application data structures. For example, your database. That's a completely different story. One example, probably the worst example I've ever encountered, was relational database gone wrong. It was a system with several million lines of Java code, and most of these million lines of Java code were written in clean code. So excellent understandability, excellent code quality, perfectly named identifiers. And then we had a look at the data structure within an Oracle database containing billions of records. So it was a huge database, not a small one, tiny one, huge. They had 5 tables 5. For a huge e-commerce system, 5 tables, a very small number. But these 5 tables each contained more than 300, 400, 500 rows each. In case you have some experience with relational databases, you know that the number of rows in a conventional relational database is something between 10 and maybe 50. 50 is already quite bad, but the average might be 20 to 30. And they had 400 or 500. The query optimizer in the Oracle database, Oracle is a standard database product. It's a rock solid system. The standard Oracle query optimizer can only handle tables with about 127, 28 rows. So the query optimizer couldn't optimize any query in the whole database. What a strange idea of building such a data model. But the initial reviewers looked only at the code and not at the data model. So you cannot optimize the code. You won't ever get rid of the problems in the database. That's another type of problem you might encounter. You won't do that. I'm really sure you won't do that. Now, again, another area where to look for problems. Misused or outdated or unsuitable technology. I brought one example. I found a YouTube video from some hardware that looked excellent. So it's very tidy. The cables are wrapped very tidy. It looks really great. If you move the video a bit forward, you see that somebody's using a CPU to cook eggs. Yes, you might do that, but it's not the intention of a CPU to cook eggs. And obviously you won't do something in your projects. What I found in real life is a rule engine, a business rule engine. It was JBoss rules, so one of these open source, but could have been any other. The expectation, the standard or default use of this technology is you have data sets where the rule engine operates on. You have data sets that are quite huge, but from these data sets you only have a few. The reason is that when you want to operate your rules upon a data set, you have to load all this data into your memory, and you don't want to do that very often. So this JBoss, or the standard use of JBoss, is optimized for few data, huge data sets. One of the systems I looked upon completely inverted this idea and had many tens of thousands of data sets, not 5 or 6, but tens of thousands. So many orders of magnitude above the default expectation from JBoss, but the data sets were extremely small. The team that implemented the system had applied the standard JBoss way of programming and was wondering about horrible performance. They misused the technology. They didn't use the technology in an appropriate way. Other examples is using old versions of your framework. So currently in PHP world, I think PHP 8 is the latest version, still sticking to PHP 2. something. I asked the team, why do you still use PHP 2. something? And they told me, oh yes, we cannot migrate to any newer version because way back we took PHP and we forked it. So we didn't use a standard language, but we forked it. We did our own PHP. What a bad idea. And we implemented many modifications, and we currently cannot merge that back to the main trunk of PHP because it's so complicated and we don't have time. So we still use a very old version a programming language. I've seen that in frameworks. People forking open source frameworks, making their own changes, don't giving that back to the open source community and sticking to these old versions. No security patches, no performance. Really bad idea. But it's a completely different way or area where to look for problems. Now, I've shown you a few areas where you might encounter specific or very strange types of problems. And I'm pretty sure there are more. There will be quality problems like performance problems. You might have problems in your processes, in your requirements processes, in your deployment DevOps processes. I didn't look at those in my talk. In reality, you should. What I left out completely is security. So information security, non-repudiability and other topics, encryption of data, backup of encrypted data, restoring encrypted data when people have lost their passwords. Again, types of problems you don't see when you only have this childish, very narrow, overly narrow focus. I'm pretty sure by now you will have found a large number of problems. For the topics we discussed mentally, I put some labels on a hypothetical breadth first whiteboard, and you will find lots of problems. You cannot fix all those. That's why I propose to use priorities. So to identify which of these priorities, which of these problems have a higher impact on your business, which of these hinder the development team more than others. As I know, in reality, we cannot fix all those. So we have to stick to the important ones. So if you look at your problems from a higher level perspective, you might find that certain problems are really bigger than others. To be able to do that, you have to have an overview of various problems and not start fixing the first problem you encounter. So it's a very, very good idea to have an analysis phase. So to use a few days, 1 or 2 days, to identify problem by area, to collect the problems and then to prioritize. How to prioritize problems is topic of another talk. It's doable. My proposal is mapping problems to money. So estimate how much money does a specific problem cost. If you calculate in time for a development team, it's kind of equivalent to money, but finding a common unit, a unit of measure, so different problems can be compared. The reason I want to do that, I want to propose that is, again, it's a business it's argument. I don't want to solve any problem when the cost for solving, so I call this improvement cost, is higher than the problem. So if you have a very trivial problem and a development team needs 3 or 4 days to solve the trivial problem, then you probably leave the problem alone, don't solve it because it's not worth the investment. By the way, at least in companies I worked for, management will surely listen if you explain that you have a problem costing the company some $1,000 per week, even when it needs a few $100s of license costs for any tool to solve this problem. Now, improvement cost should be lower than the cost of the problem, the cost that the problem is producing. Only now, when we have an overview of the problems, we have priorities, maybe we have pinpointed a value, a money value to our problem, so we know how expensive a specific problem is, then we can start changing the system, or we can start improving. My proposal, very brief today, is do that continuously. So the large cloud you see on my slide is the day-to-day development. So you continue delivering features, doing day-to-day development work, and parts of your time you should invest in improving, in solving some of these problems you identified beforehand. And in this AIM improvement method, I talked about architecture improvement method. We categorized various methods, various approaches for changing. I want to focus today on changes in the large-scale restructurings. And I brought you a few examples. One is called extraction. Extraction means reducing the size of your system by pulling out things that don't belong in there. Why is reducing the size a good idea? Currently, nearly large parts of the world are talking about microservices or self-contained systems. Being able to build and deploy and operate smaller systems makes you faster. It decreases development time, increases velocity or speed, how you can deliver features. So it might be a good idea to look in this direction, and it's simpler if your systems, your services are smaller. One aspect or one idea to get things smaller is to extract everything that's not required for the core idea of the system. And the overall pattern, the architectural improvement pattern, in this case is called change by extraction. So have a look at your system. Is there anything contained in your system that doesn't really belong there? One specific thing I found in many systems is an area called util. The util package in Java is often a good candidate for extraction. If it belongs to your core domain, you don't need to call it util. So you might refactor the utils out in some frameworks or libraries or even other services. So you can reduce your system. You'll have a utility package or utility system, but it's very easy. It's way easier to optimize smaller systems than larger. So extraction is one way. Another way is having a look at your user groups or your clients using your system. I encountered various occasions where we had completely different kinds of clients using the system, but we had the systems were built for both or many types of clients, and you might split, for example, private customers, corporate customers, customers buying cars and customers buying food. Splitting your system means you can reduce the splitted system by everything that's not required for selling cars, or you can reduce the food system by everything that's not related to food. Now you have two systems, but both are way smaller than the original one, making them easier to handle, simpler to understand. A third tactic or strategy to improve systems is to strangle out. Originally it was called Strangulizer. It's a very morbid idea of strangling software, but the metaphor is quite easy to understand. By building up small parts, probably in a new technology and a better architecture, routing calls to your software over the time more and more to the new system, to the new parts of the system, and by that way strangulizing or reducing the importance of the old to the new. That's definitely not restricted to web systems like the original author Paul Hammond proposed. You can do it in all kinds of systems. It's called strangulizer or strangler fig pattern. Martin Fowler has written about that extensively. I applied that various times, and based upon this idea is the last I want to show you is the decorating collaborator. You have some client code using some kind of supplier, but the supplier, the service is really in a bad shape. So it's I call it flawed. You want to get rid of it, or you don't want to modify it again. But some business says, oh, I need new features. One idea could be you introduce some abstraction, you introduce some facade, or I call it proxy in this case. The proxy just delegates a conventional call to the existing flawed system. Now you implement additional functionality in better, newer, more recent technology, and the proxy becomes a bit more intelligent. The business process requires the existing and some new, and the proxy coordinates the old and the new. By that way, you can keep the existing often without any change, but still you can enhance functionality by adding new in a more appropriate technology or more appropriate architectural structures. This decorating collaborator looks very simple on paper. In practice, if you need common data, it's a bit more complicated, but it's a very, very elegant way of strategically improving systems without having to cope with this existing COBOL code, at least for a while. With the decorating collaborator, it's not simply possible of getting rid of the flawed one. Then you have to combine methods. Now, everything I said about improving systems was related to code, or code and architecture, code and structure. In real life systems, at least in information systems, not in embedded or real time, but in information systems, web systems, online systems, you have a database. You will surely have a database, and improving databases is really way more difficult. I cannot go into detail here. My time's nearly over, but beware of the database. If you estimate how long does an improvement or a change take, changing databases takes ages, because very often it's not only your database. Other people might also use it. So beware of that. And our time is over. It's way too short. Let me give a summary. You need to identify in breadth types of problems you have. You have to look for code. You have to look in architecture, structure, component structure. You have to look for technology. You have to look at your data, and so on and so on. I gave you some examples. The search is not over. I didn't cover security at all. I didn't cover processes at all. In all these areas, you might have problems. When you collected problems, find priorities. Handle the most important problems that are most often the most value-reducing problems that cost the most effort, really bad stuff. Solve those. But only after we have an overview of the problems. That's why 3 steps are important: identify, prioritize, and only then change. 44 minutes, 45 seconds. Thank you very much for being here with me. I immensely enjoyed being in Moscow. Too bad I'm not really in Moscow. One day when traveling becomes easier again, we'll hopefully meet in person in any of the conferences next year. Thank you very much for having me here. While I talked, I couldn't look at the chat.
Yeah,
I'll do that right now.
Thank you. Thank you. And we have one question from Alexander Makarov. He's not speaker. I hope Alexander. Oh, yeah. Please ask yourself.
Okay, hello. And first of all, thank you for the talk. I've really enjoyed it. And the question is about the very beginning of the talk. You told us about not falling for new shiny technology, but isn't easier hiring and, well, being more attractive a business value by itself?
Yeah, you are perfectly right that all the companies I know, and I'm working as a consultant, I'm traveling around seeing many companies, hiring people is a really important issue. And take one of the last slides I showed, this decorating collaborator. It's perfectly possible to apply new technology together with existing technology. Let the guys you hire work on the fancy frameworks, let them deliver small parts of features and fancy technology. If this is a solution to your hiring problem. So it might be a very valid. We have many existing COBOL systems in Germany, and it's extremely difficult to find COBOL programmers. And yeah, I know what you are talking about. Great question.
Oh, thank you, Dr. Starke. It was wonderful, and in chat there's a lot of thank you, great, thank you, excellent talk, thank you, and so
yeah,
on.
you really make my day. I will have a look at all these thank yous.
It's great.
Excellent.
Thank you. And now, what show must go on. And thank you. You can turn your camera and microphone off. And
yeah.
And thank you. Thank you. And stop share screen, please.